Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. Friday evening. The launch promo just went out. One EC2 instance is running the entire web store. Traffic spikes. The box freezes. Every customer gets a timeout. Part 8 gave you auto scaling. Today, we put a traffic cop in front of it. By the end, you will be able to name the elastic load balancing types AWS offers, match each one to the right workload, configure a health check and a listener rule, and explain how a load balancer can work with auto scaling. Part 8 gave you a self-scaling fleet. Today, we make that fleet reachable. One important detail up front: a load balancer can stop routing new traffic to an unhealthy target. An auto-scaling group can replace that target only when you attach the load balancer to the group and enable elastic load balancing health checks for the group. That distinction matters in the real world and on the exam. A load balancer is the traffic routing layer between clients and your application targets. With one server, there is nothing to distribute. That server is a single point of failure. Add 2 or more targets across availability zones, and a load balancer can normally route new traffic to the healthy ones when another target fails its configured health checks. The word normally matters. A load balancer is not a magic shield. If every target in a target group is unhealthy, application load balancer and network. Load balancer can fail open and route traffic to all registered targets rather than having nowhere to send it. The real availability design is bigger than add a load balancer. You need healthy capacity across multiple availability zones, meaningful health checks, and an application that can actually recover when a target fails. AWS offers several elastic load balancing options, but they solve different problems. Application Load Balancer, or ALB, is designed for HTTP and HTTPS applications. Because it understands web requests, it can make Layer 7 routing decisions based on things such as hostname, URL path, HTTP headers, query strings, and other supported request details. That makes ALB a natural choice for websites, web APIs, and microservices that need request-aware routing. Network Load Balancer, or NLB, operates at the network layer. It is designed for high-performance TCP, UDP, and TLS workloads and provides static IP addresses for enabled availability zones. Use NLB when the requirement is more about network connections, very high throughput, static addressing, or protocols that don't need HTTP-aware routing. Gateway Load Balancer, or GWLB, is more specialized. It helps route traffic through virtual network appliances such as firewalls, intrusion detection systems, intrusion prevention systems, and other security or inspection appliances. Then there's Classic Load Balancer. That's the older generation. Know that it exists, especially when you encounter older environments, but treat it as a legacy option rather than the default choice for a new design. For this beginner lesson, the 2 most important load balancers to understand are ALB for request-aware HTTP and HTTPS routing, NLB for high-performance network-level traffic. Don't memorize them as web equals ALB. Everything else equals NLB. Start with the protocol, routing requirement, availability design, and client requirements. Then choose the load balancer that matches them. ALB is built for HTTP and HTTPS, so it can inspect the web request and send traffic to different destinations based on what it finds. A listener waits for traffic on a port you choose. When a request arrives, a rule evaluates the request details you specify. For example, the URL path the client asked for. If it matches, the action forwards the request to a target group. The target group is simply the pool of servers or containers that will handle the request. Same load balancer, different request path, completely different destination. Time for a quick recall check. Which AWS load balancer type is built for raw TCP and UDP traffic and gives you a static IP address? The Network Load Balancer, NLB. If you said Application Load Balancer, remember ALB is built for HTTP and HTTPS and makes routing decisions from the web request, while NLB is the one you reach for raw TCP and UDP at very high throughput. Gateway Load Balancer is the specialist. It's designed to send traffic through security appliances before it ever reaches your application, so you can inspect and filter it. Classic Load Balancer is the older option. Know it exists, then treat it as legacy. For new designs, the two you'll actually reach for are Application Load Balancer and Network Load Balancer. Quick recall check. Which AWS load balancer type routes based on the URL path or hostname a client requests? The Application Load Balancer, because it's built for HTTP and HTTPS, and can make routing decisions from those request details. Network Load Balancer is built for raw TCP and UDP, so it doesn't route based on web request details. Before we open the console, two quick definitions. A VPC is your private AWS network. Availability zones are separate infrastructure locations inside an AWS region. Here is the ALB skeleton. A listener waits for traffic on a protocol and port you choose. When an HTTP or HTTPS request arrives, the Application Load Balancer evaluates listener rules in priority order. A rule can match request details such as the hostname, path, HTTP headers, query strings, source IP, or request method. If a rule matches, its action can forward traffic to a target group, redirect the client, or return a fixed response. A target group is the registered set of targets that handles the traffic. Those targets might be EC2 instances, IP addresses, containers behind IP targets, or Lambda functions in supported designs. Every listener also has a required default rule. It runs last when no higher priority rule matches. That is the useful mental model. One listener, many ordered rules, one required default action, and one or more target groups. Now let's create an application load balancer in the AWS console. Open the EC2 console, find Load Balancers. Then start the Load Balancer creation workflow. Choose Application Load Balancer. Give the load balancer a meaningful name. For this lab, we'll use an internet-facing load balancer because clients will connect from outside the VPC. Next, select the VPC where your application targets run. Then select subnets in at least 2 availability zones for a resilient lab design. Now configure the load balancer's security group. Allow only the client traffic your application actually requires on the listener port. For example, if you're serving HTTPS publicly, that may mean allowing TCP port 443 from the client networks you're intentionally serving. Don't interpret this step as always open the web port to the entire internet. The correct source range depends on the application. Now, create or select a target group. A target group is where the load balancer sends traffic after a listener rule matches. Register your EC2 instances as targets. Then configure a listener, for example, HTTPS on port 443, or HTTP on port 80, depending on your lab. The listener receives client traffic and evaluates the listener rules. Finally, create the load balancer. Once it becomes active, copy its DNS name and test the application. Then open the target group and verify that the registered targets become healthy. Don't stop after you see the web page. Check Listener Rules, Target Group, Target Health, Security Groups, Availability Zones. That's how you learn what the load balancer actually built, not just how to finish the wizard. Now let's look at the same basic workflow from the AWS CLI. The exact parameters depend on your VPC, subnets, security groups, target type, and region. So don't memorize a giant command from this video. Learn the sequence. Step 1. Create the load balancer. The command begins with AWS LBv2 create load balancer. Here you provide things such as the load balancer name, subnets, security groups for an ALB scheme, and load balancer type. Step 2. Create the target group. Use AWS ELB v2 create target group. The target group defines things such as protocol, port, VPC, target type, and health check configuration. Step 3. Register the targets. Use AWS ELB v2 register targets. This associates your EC2 instances, IP addresses, or other supported targets with the target group. Step 4. Create the listener. Use AWS ELB v2 create listener. The listener receives client traffic on a protocol and port and defines the default action. For example, an HTTPS listener might forward requests to the target group you just created. So the CLI flow is create load balancer, create target group, register targets, create listener. Then verify the deployment. Use commands such as describe load balancers, describe target groups, and describe target health to inspect what AWS created. The stable lesson is not the exact command flags. It's the architecture sequence, load balancer, listener, target group, registered healthy targets, AWS ELB v2 create load, balancer AWS ELB v2 create target, group AWS ELB v2 register, targets AWS ELB v2 create listener, AWS ELB v2 describe target health. Here is the problem a health check solves. An instance's operating system can still be running even when the application is frozen or unable to serve its traffic. Without a target group health check, the load balancer has no application-level signal that tells it to stop routing new requests to that target. For an application load balancer, the target group periodically sends an HTTP or HTTPS health check request to the configured path and port. After the target fails the configured number of consecutive checks, the load balancer marks it unhealthy and normally stops routing new traffic to it. When the target passes enough consecutive checks again, it returns to service. But understand the boundary. The load balancer only knows what the health check reports. If all targets in the group become unhealthy, ALB can fail open and route traffic to all of them. That is why health check design must be deliberate. Not just a random health endpoint copied from a tutorial. Quick recall check. What does a target group health check actually do? It tells the load balancer whether a registered target should normally receive new traffic. When a target fails enough configured checks, it is marked unhealthy and taken out of normal routing until it recovers. It does not repair the application. It does not automatically replace the EC2 instance by itself. And it only measures the condition that your configured check can observe. The settings look boring until you get one wrong. The most common mistake is using a health check path that proves almost nothing. A plain route page may return 200 because the web process is alive, even though the application cannot complete important work. But there is an opposite mistake too, making every load balancer health check perform a costly or fragile test of every downstream dependency. If one shared database outage makes every target report unhealthy, you can remove all targets from normal routing at the same time. And an ALB may fail open anyway. Choose the health check based on the traffic the target group serves. A lightweight readiness endpoint should confirm that the instance is ready to accept the routed request. Keep it fast, deterministic, and inexpensive. Use separate monitoring, synthetic checks, and alarms for broader dependency health when a failing dependency should not automatically eject every target from the load balancer. Then tune the interval, timeout, thresholds, and success codes to match the application's startup time, normal latency, and failure tolerance. The point is not to make a check strict. The point is to make it meaningful. Here is the nuance almost everyone misses. A target can return a healthy response and still fail for some real user requests. The process may be alive. The basic readiness endpoint may work. But a particular database query, payment provider, feature flag service, or downstream API may be failing. That does not mean the load balancer health check is useless. It means one health check cannot be every kind of monitoring. Use target group health checks to decide whether a target should receive the traffic routed to it. Use application metrics, synthetic transactions, dependency checks, logs, traces, and alarms to detect broader service problems. A good health endpoint is not a lie detector that only sees a heartbeat. But it also should not create a cascade where every target is ejected, because one shared dependency has a temporary problem. A listener rule does not have to send every request to the same destination. You define conditions and actions. Conditions can match the host header, the domain a client requested, a path pattern, HTTP headers, query strings, source IP, or other supported request properties. Actions can forward traffic to a target group, redirect the client, or return a fixed response. So a checkout subdomain can route to a checkout target group, while an API path routes to a backend target group. Rules are evaluated in priority order. More specific rules should have higher priority than broad catch-all rules. And every listener has a default rule. It cannot be deleted, and it runs last when no higher priority rule matches. Make that default action intentional, forward to a sensible target group, return a fixed 404 response, or redirect where appropriate. If you ever read an ALB rule in CloudFormation or the API, this is the shape that matters. Conditions decide whether the rule fires. Actions decide where traffic goes. Priority helps define evaluation order, so more specific conditions can be ordered ahead of broader ones, but check current AWS documentation for the exact semantics before you memorize a rule. Quick recall check. How would you route requests for checkout to a separate checkout service? Create a higher priority application load balancer listener rule with a path condition of checkout and a forward action to the checkout target group. Requests that do not match that rule continue through the listener's required default rule. That is the ALB pattern to remember. Conditions decide whether a rule matches, actions decide what happens next, and priority decides which matching rule wins. When you need to choose between an application load balancer and a network load balancer, start with two questions. What protocol am I handling? And what routing behavior do I need? Start with Application Load Balancer. ALB is designed for HTTP and HTTPS applications. It can make routing decisions using Layer 7 request information such as host names, URL paths, headers, query strings, request methods, and other supported HTTP details. That makes it a natural fit for websites, REST APIs, and microservices where one load balancer may route different requests to different services. Now look at Network Load Balancer. NLB works at the network layer and supports high-performance TCP, UDP, and TLS workloads. It is worth investigating when requirements include static IP addresses, very high connection or flow throughput, TCP or UDP traffic, network-level connection handling, or TLS pass-through where the backend must handle the encrypted connection. But don't use one keyword to make the entire decision. For example, seeing TLS does not automatically mean NLB. ALB also supports HTTPS and can terminate TLS at the load balancer. The question is, do I need Layer 7 HTTP aware behavior or Layer 4 network behavior? A useful beginner heuristic is HTTP HTTPS plus host or path routing. Investigate ALB. TCP UDP, static IP requirements, TLS pass-through, or network layer performance. Investigate NLB. Then validate. Client IP requirements, TLS behavior, static addressing, target type, cross-zone behavior, performance, and cost. The shortcut helps you narrow the options. The requirements make the final decision. Elastic load balancing pricing is usage-based, not a single fixed line item. For Application Load Balancer, you pay for each hour or partial hour the load balancer runs plus the load balancer capacity units, LCUs, the ALB consumes. The LCU dimension that costs the most in an hour determines the usage charge. It can reflect new connections, active connections, processed bytes, or rule evaluations. For Network Load Balancer, you pay for load balancer hours plus network load balancer capacity units, NLCUs, based on connections or flows and processed bytes. Standard AWS data transfer charges and public IPv4 charges can also apply. Gateway load balancer endpoints, databases, NAT gateways, logging, and the targets behind the load balancer can add further architecture costs. Do not use a third-party monthly price as a universal budget. Pricing depends on region, hours, traffic, protocols, rules, and the surrounding architecture. Use the AWS pricing calculator and current regional pricing before you launch, and delete lab resources when you are finished. Cross-zone load balancing controls. Whether a load balancer node can distribute traffic only to targets in its own availability zone or across healthy targets in all enabled availability zones. With it enabled, traffic can be spread more evenly when one zone has fewer targets than another. With it disabled, each load balancer node routes only to targets in its own zone, so you need enough healthy capacity in every enabled zone. The default depends on the load balancer type. For an application load balancer, cross-zone load balancing is enabled at the load balancer level. A target group setting can override that behavior if you intentionally turn cross-zone routing off for that target group. For a network load balancer and gateway load balancer, cross-zone load balancing is disabled by default. You can enable it when the architecture needs it, but with NLB you should also understand the related interavailability zone data transfer cost. The rule is not always turn it on. The rule is plan enough healthy target capacity in every enabled availability zone, then choose the cross-zone setting that matches your availability, traffic distribution, failure domain, and cost requirements. TLS termination is one reason backend servers do not have to manage the public certificate and TLS negotiation for every client connection. With an HTTPS listener, an application load balancer can terminate the client's encrypted connection using a certificate you attach to the listener. That gives you a central place to manage certificates and TLS policies while the backend application focuses on the business logic. But TLS termination at the load balancer does not automatically mean the connection to the targets is encrypted. If your architecture requires encryption on that hop too, configure HTTPS from the load balancer to the targets and make sure the target certificates and application settings are correct. Then lock the network down. For an internet-facing web application, the load balancer's security group can allow HTTPS from the clients you intend to serve. The backend EC2 security group should allow its application port from the load balancer's security group, not from the entire internet. That creates the correct boundary. Clients reach the load balancer, and the load balancer reaches the backend. Clients do not bypass your routing, TLS, health check, and observability layer to reach the instances directly. Two-part load balancer checkpoint. Question 1. You have an internet-facing application load balancer in front of two EC2 application servers. Should the backend EC2 security group allow the application port directly from the entire internet? No. In a common ALB architecture, the backend security group should allow the application traffic from the load balancer's security group. That creates an important boundary. Clients connect to the load balancer. The load balancer connects to the backend. The backend is not directly exposed to public clients. That means users cannot bypass listener rules, TLS handling, health check routing, and the observability layer provided by the load balancer. Question 2. One registered target repeatedly fails the target group's configured health check. What does the load balancer normally do? It marks the target unhealthy and stops sending it normal new traffic while healthy targets remain available. But remember, the load balancer does not repair the application, and it does not automatically guarantee that an auto-scaling group will replace the instance. Replacement requires the auto-scaling integration and health check configuration we will review later. Remember the responsibilities. Security groups control who can connect. Health checks control which targets normally receive traffic. Auto-scaling can replace unhealthy capacity when configured to use the relevant health signal. Most people stop after the target group is created. Do not. Open the target group and review its health check configuration. Set the protocol, port, and path to a lightweight readiness endpoint that proves the target is ready to serve the traffic routed to that group. Avoid an endpoint that always returns success without considering whether the application can serve the request. But also avoid making the load balancer run an expensive test of every shared dependency on every check. For an application load balancer, review the interval, timeout, healthy threshold, unhealthy threshold, and success code matcher. Set them from your application's actual behavior, startup time, normal latency, transient error rate, and recovery requirements. Then test failure cases. Confirm that a target is marked unhealthy when it should be, that a new target has time to start, and that the application stays available when one target is removed from normal routing. A health check is not a box to tick. It is part of the availability design. What happens when a target needs to leave service? Maybe you're deploying a new version. Maybe auto-scaling is scaling in. Maybe you're intentionally deregistering an old target. You usually don't want the load balancer to keep sending new work to a server that's about to disappear. But you also don't necessarily want to terminate active work immediately. That's where connection draining, represented by the target group's deregistration delay, comes in. When a target begins deregistration, the load balancer stops sending it new traffic according to the applicable load balancer behavior. The target enters a draining state while existing in-flight work can finish. For application load balancer target groups, the documented default deregistration delay is 300 seconds. But that doesn't mean every application should use 5 minutes. Configure the delay around your real workload. Ask, how long can a valid request take? Does the application use long-lived connections? What happens during deployment? How quickly must failed capacity be replaced? And how does the particular load balancer and target type handle draining? If the delay is too short, valid in-flight work may be interrupted. If it's unnecessarily long, deployments, scale-in, or replacement workflows can take longer than needed. And if a target has no relevant in-flight requests or connections, deregistration may complete sooner than the full configured delay. Remember, draining doesn't fix an unhealthy application. It gives existing work a controlled opportunity to finish while new work is directed elsewhere. Test the behavior with the actual application. Don't simply accept the default because it's the default. 5 mistakes quietly break applications behind a load balancer. 1. A health check that returns success even when the target cannot serve the traffic it receives. 2. The opposite extreme. A health check that turns every shared dependency issue into a signal to eject every target from normal routing. 3. A backend security group that still accepts traffic from anywhere, allowing users to bypass the load balancer. 4. Assuming that cross-zone behavior is the same for every load balancer. ALB is cross-zone at the load balancer level. NLB and GWLB start with it off by default. 5. Setting a deregistration delay without understanding the application's longest requests and connection behavior. Fix all 5 before you call the architecture production ready. Instant recall. Your health check path returns a success response, but a downstream database is unavailable. What does the load balancer know? It knows only what the configured health check proves. If the endpoint returns a successful response without testing the condition that matters for the routed traffic, the target can remain healthy, even while real user requests fail. But do not jump to make every check query the database. Decide whether loss of that dependency should remove the target from normal routing. Use the load balancer health check for target readiness. Then use monitoring and synthetic checks to detect broader dependency failures. Here is the highly available pattern worth sketching from memory. An auto-scaling group launches EC2 instances. When the group is attached to a load balancer or target group, it registers those instances. The target group performs health checks and routes normal traffic to healthy targets. By default, the auto-scaling group uses EC2 health checks and ignores elastic load balancing health results. If you explicitly enable elastic load balancing health checks for the auto-scaling group, then an instance that the attached load balancer reports as unhealthy can be marked unhealthy by the auto-scaling group and replaced. During replacement, deregistration delay can give in-flight requests time to complete before the instance is terminated. So the complete loop is launch, register, health check, route, detect failure, mark unhealthy, drain, replace, and register the new instance. The word to remember is configured. The loop works because you deliberately connect the load balancer, target group, health checks, and auto scaling group. Elastic load. Balancing is a great portfolio topic because one small project can demonstrate several cloud skills at once. You can show networking, high availability, security groups, health checks, monitoring, auto scaling integration, DNS, and cost awareness. Here's a project you can actually build. Launch 2 small EC2 application targets in separate availability zones. Put an application load balancer in front of them. Configure an HTTPS or HTTP listener for your lab. Create a target group. Register both targets. Configure a meaningful readiness health check. Restrict the backend security group so the application port accepts traffic from the load balancer rather than directly from the public internet. Now test failure. Stop the application process on one target or otherwise make the health endpoint fail in a controlled lab. Watch. Target health, CloudWatch metrics, application behavior, and traffic routing. Then restore the target and observe recovery. If you connect the targets through an auto scaling group, go one step further. Enable the appropriate elastic load balancing health checks for the group. Then observe the difference between load balancer removes target from traffic and auto scaling replaces unhealthy capacity. Finally, document the architecture diagram. Listener rules. Target group. Health check configuration. Security group flow. Auto scaling integration. And what happened during the failure test. That's much stronger than saying, I know what an ALB is. You're showing that you understand how traffic reaches an application and what happens when part of the application fails. Once traffic is flowing, watch the metrics that match your load balancer type and application behavior. For an application load balancer, useful signals commonly include request count, target response time, HTTP 4XX and 5XX errors, rejected connections, processed bytes, and healthy and unhealthy target counts. For a network load balancer, focus on connection or flow behavior, active flow counts, new flow counts, processed bytes, TCP resets, unhealthy target counts, and rejected connections where applicable. Do not memorize a list without context. Start an incident with the symptom. Are users receiving errors? Are targets unhealthy? Are connections being rejected? Is latency rising? Or did traffic jump unexpectedly? The unhealthy target count is an important signal, but it is not the whole diagnosis. A target can be healthy while serving application errors, and an entire target group can be unhealthy during a wider dependency incident. Combine load balancer metrics with application logs, traces, database metrics, and auto-scaling activity. When you are staring at a target group and need to know why a target is not receiving normal traffic, use describe target health. The command shows each target state, such as healthy, unhealthy, initial, draining, or unused, and often includes a reason code. For an application load balancer, examples include target.timeout, target.response code, mismatch, and target.failed health checks. A result of unhealthy tells you that the target is not passing the target group's configured health checks. It does not automatically prove that the instance is stopped, that the auto-scaling group will replace it, or that every user symptom has the same cause. Check the health check path, port, security groups, application logs, target registration state, and availability zone. Then check the Auto Scaling group configuration separately to see whether elastic load balancing health checks are enabled for replacement. Here is the trap to avoid. EC2 status checks are designed to detect problems with the virtual machine or its underlying infrastructure. An application can be broken even when the EC2 instance appears healthy. Elastic load. Balancing health checks test the configured target protocol, port, and path. For an application load balancer, that can give you an application-level signal. A timeout or a response code mismatch can mark the target unhealthy and stop normal routing to it. But the load balancer does not automatically cause EC2 replacement by itself. To have Amazon EC2 Auto Scaling use that signal, attach the load balancer or target group to the Auto Scaling group and explicitly enable elastic load balancing health checks for the group. Then, when ELB reports a registered instance unhealthy, Auto Scaling can mark it unhealthy on a subsequent health check and replace it. Use EC2 checks to protect the host. Use target group health checks to protect traffic routing. Configure Auto Scaling integration when you want application-level target failure to trigger replacement. Final health check checkpoint. You have an EC2 instance behind an application load balancer. The EC2 instance passes its EC2 status checks. The operating system is running, but the application has a problem. Every request to the application's health endpoint returns an HTTP 500 error. Which health signal can detect that application-level failure? The target group's elastic load balancing health check. EC2 status checks focus on the health of the instance and underlying infrastructure. They don't necessarily know whether your application is returning valid responses. An application load balancer health check can probe the configured protocol, port, path, and expected response codes. If that application check repeatedly fails according to the configured thresholds, the target can be marked unhealthy and removed from normal routing. Now, question 2. Does the load balancer marking that target unhealthy automatically guarantee that the auto scaling group will terminate and replace the EC2 instance? No. For Amazon EC2 Auto Scaling to use the load balancer's health result for replacement, you need the integration configured appropriately. The target group or load balancer must be attached to the auto scaling group, and elastic load balancing health checks must be enabled for the group. Then ELB reported application failure can become a replacement signal. So remember the 3 roles: EC2 status checks, host and infrastructure health, ELB target health checks, whether the target should normally receive application traffic, auto scaling, capacity maintenance and replacement when configured to consume the appropriate health signal. That's how the pieces work together. Let's put the whole pattern on one map. A client looks up your domain in Route 53. An alias record can point that friendly name to the load balancer's DNS name. The client connects to a load balancer node using one of the addresses returned by DNS. For an HTTPS application load balancer, the listener can terminate TLS, evaluate listener rules, and forward the request to the selected target group. The target group performs health checks and normally routes traffic to healthy registered targets across the enabled availability zones. An auto-scaling group launches and registers EC2 instances with the attached target group. If you enable elastic load balancing health checks for the auto-scaling group, ELB reported target failure can also trigger the group's unhealthy instance replacement process. That is the architecture to sketch from memory: client, Route 53, load balancer, listener rule, target group, healthy targets across availability zones, and an auto-scaling group that creates and, when configured correctly, replaces the instances. 3 takeaways from everything we covered. First, use an application load balancer for HTTP and HTTPS traffic when you need request-aware routing. Use a network load balancer for high-performance network traffic, such as TCP, UDP, or TLS, where Layer 7 request routing is not the requirement. Second, a health check protects traffic routing only to the extent that it measures the right condition. Build a lightweight readiness check for the traffic you serve, tune it to real application behavior, and use broader monitoring for dependency failures that should not eject every target at once. Third, elastic load. Balancing and auto-scaling become a self-healing pattern only when you connect them deliberately. Attach the target group to the auto-scaling group and enable elastic load balancing health checks if ELB reported target failure should lead to instance replacement. Then test the design. Break one target. Confirm that new traffic stops going there. Confirm that the remaining targets have enough capacity. And confirm that the auto-scaling group's replacement behavior matches the health check settings you intended. Next in this series, Route 53. You've built the load balancer, now point a real domain name at it. We'll map a clean name like yourstore.com to the ALB you just created, set health checks at the DNS layer, and stop handing users that ugly AWS URL. If you're prepping for Cloud Practitioner, keep going. The next part builds directly on today's ALB, and it's where the architecture starts to feel like a real product. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.